discuss what an allotrope is, and then we'll move to the types of molecules. Now, allotropes is a type of relationship between two molecules that says that, I'll just read it out. The different modifications of the same element gives you the concept of allotropes. Now, how do we exactly understand what an allotrope is, right? So, if you have oxygen, atoms, now two oxygen atoms can come together and can give you the oxygen molecule, the dioxygen molecule. It can become O3, right, and become ozone. It can also become O4 or O8. So all of them are made up of oxygens. But they have different numbers and different structures and different properties based on the type of arrangements that they have and based on the number of atoms that are there. So they are from the same element, they are made up from the same element, but they have different properties, they behave differently. Another very famous example is carbon, right? So you know coal is carbon, graphite or coal, right? These are slightly different definitions, but okay. Coal, graphite, diamond is also C, right? All of them have the chemical formula as C, but they are allotropes. The same for sulfur. So sulfur can be S2, can be S6, can be S8, and things like that. You can have phosphorus, you can have red phosphorus, white phosphorus, black phosphorus, and things like that. In here you can have more. So oxygen basically has these four. Phosphorus has 6 allotropes that are listed. Carbon have at least 12 allotropes that are listed. So these all are made up of the same element, carbon, but they have different properties. Their structure, organization is different. So this relationship is called allotropy, and these become the allotropes of each other, right? And the allotrope comes from the Greek word allos means other, and tropos means way. So the other way of like arranging the same elements to give you different kinds of molecules, and this is basically called allotropes. Now in future you will also learn about a concept called the polymorphism. Okay, now some people study allotropes as a special case of polymorphism. Now what is polymorphism? So polymorphism is a similar case in which you can have the same elemental composition, but the structures will be different. For example, you can have silica, you can have SiO2, but the structure and the properties and the densities and all the different kinds of things that define a compound will be different. So SiO2 can be either become crystalline and it can become quartz. It can also be amorphous and become amorphous silica. And there can be other polymorphs of silica. There can be coesite. So if you have silica exposed at high pressures, so you form coesite. So at places in which you have meteorite impact. So imagine there is a place on Earth and you have a meteorite impact, and if you go there and find out the silica, you will not find quartz, you will not find amorphous silica, but you will find coesite. Why? Because it is that polymorph of silica which forms at high pressures, right? So you get the idea of polymorphism, right? The same chemical formula but different structure. So it is similar to this. Although the chemical formula is not same, so there are some disputes between that, how to exactly differentiate between, like how allotrope can be considered as a special case of polymorphism. Some people say that no, okay, some chemists do this entirely differently, that okay, O2, O3, O4, they don't have the same chemical formula, but they're from the same element made up of different number of atoms. So let's call this allotrope and keep that polymorphism thing separate, because it's entirely different based on they have the same chemical formula. SiO2 is same, but it will have different properties. Okay, but in here you see coal is C, graphite is C, diamond is C, and there are others, right? So you just know that there is a thing called allotropy, in which this thing goes on, and there is a thing called polymorphism. We'll discuss about those things later. That is polymorphism, and there's also one thing called the isomorphisms and things like that. Okay, isotopes and isomorphism, things like those. So we'll discuss about those things, but you just a good thing to know that there are allotropes, and these are the different allotropes that exist. Okay, now when we discuss these things, now this brings us to the topic of types of molecules. Now, if a molecule is made up of the same kinds of atoms, like in here, what are the types of atoms involved in this? It's just oxygen, right? It's just O, O, O. So there's no other thing. So in here, like if you have O2 or O3 or N2 or P4 or S8, right? Only one type of atom constitute this molecule. So that molecule will become a homoatomic molecule. Okay, so that becomes a homoatomic molecule. What's the reverse of that? Heteroatomic, right? It's extremely simple. So if a molecule is made up of two or more kinds of atoms, it becomes heteroatomic, like H2O, I don't know, CH4, H3PO4, and things like that. So it's really simple. Homoatomic made up of same kinds of atoms, and heteroatomic made up of different kinds of atoms, right? Two or more different kinds of atoms. Now, the idea about these molecules become a little fuzzy sometimes, but yet it is an important idea. It's an important concept. Why does it become fuzzy? This becomes fuzzy because, like, let's say you have water, right? So you have water in a glass or a beaker. Now, when does one molecule end, and where does the other molecule start? It's a very fuzzy line there. Why? Because say you have this, okay, let's assume we have this atom of water, molecule of water, H2O. Now, this oxygen atom is also attracted to the hydrogen in here. Why? How? We'll see. So this bond of oxygen and hydrogen is called a hydrogen bond, and we'll study about types of these kind of interactions in a subsequent lecture. But in here, just understand that this oxygen molecule, this water molecule, is not standalone. This is interacting. This has some kind of interactions with its neighboring molecules. This is attracted to this. This is attracted to this, to this, to this. All these kinds of different attractions are there. Where does this attraction end? Where does its attraction start? Right? All these kind of things become fuzzy at the molecular level. Nevertheless, molecule is an extremely powerful concept. Why? Again, now, so you say that, okay, there is an attraction here. So what makes this unit very special? Because this bond is not that strong, right? This is a very strong bond, and the oxygen and hydrogen in this bond, so the hydrogen and oxygen, the distance between this hydrogen and this oxygen is really small. So this hydrogen is really close to this. However, this hydrogen and this oxygen has some kind of interaction, but this distance is far as compared to this distance, right? So whatever interactions are there, the concept of molecules become important, because this still can behave like as a separate entity, because they're so close to each other. Okay, all right. In this, when we touched upon this idea of a molecule, now there is also an idea about ions in water. Like, so you saw the different kinds of ions, right? So let's take a simple ion called the H+. Like H+ can exist. Now this H+ can be in water. So you can have H+ in water. We do have H+ in water, right? The thing is that this H+ is not a separate quantity inside water. These form associations, and pretty decent associations, and which makes it difficult for this H+ to exist independently. More so than this are the cations. So say you have Na plus or Mg plus, Mg2 plus or Fe2 plus, things like that, or Fe3 plus. You will never have Fe2 plus ions in water, like separate Fe2 plus cations in water. You cannot, it doesn't exist. What happens is this Fe2 plus attracts H2O molecules around it, right? So this becomes, so there is another H2O coming in from here, another H2O coming in from here, another H2O coming in from here, water, okay? So you can have different kinds of, so basically Fe2 plus doesn't actually exist in a solution. What actually exists are some kind of complicated structures in which this H2O becomes a part of that. So this becomes a complicated structure like this, okay, 6. So this becomes a complicated structure like this. So this happens generally with the cation. So we have to understand that, okay, cations, like water in here did not exist as one unit. There was some kind of attraction going on in here too. All these cations don't generally exist as sole cations inside water. People do not understand it until very later in their courses. But I think this is an important concept to understand, that although we have Na plus, so this Na plus can exist as a single quantity if you have it in the gaseous state. But if you have this Na plus in the solution state, it is almost impossible to have an Na plus ion just floating around in the solution without H2O surrounding, like making a layer on that. And this layer is not a diffuse layer, this is a pretty strong layer, which makes this a very stable entity. So this can exist. You can see this whole thing floating around. Now, there will be another layer. So this becomes, so if you have the Fe here, and then you form the H2O molecule here, so this becomes a pretty stable entity, which is this. Now there can be diffused H2O layers too. So there can be mild interactions in this diffused layer, right? But this diffused layer like dies off with the distance. The more you move out, that distance, like that interaction dies off. But the inner core is extremely stable. So we should understand this concept, right? And this will become extremely important in subsequent lectures when we actually deal with H plus. So if you remember, like H plus is basically related to the definition of an acid, right, which we'll read. So these things will become important. Like if H plus doesn't exist in liquid state, what does, right, is actually H3O plus. Like H plus is combined with a water molecule and it forms an H3O plus, the hydronium cation, and that is the stable part. And even that hydronium ion is attracted to water, and they can form even bigger positive charge sets of ions. But H plus doesn't exist. Mg2 plus doesn't exist. Fe2 plus in water doesn't exist. If you have this in water, it will not exist as sole ions. They have to have some kind of association with the water, and this is very important to understand. Now, if you change the solvent, you'll have a different solvent coming in and making these associations. So if it is water, we call it hydration. If there is some other ion, if this solvent is something other, like ammonia or say alcohol or something like that, so if you have a different solvent, you'll call it solvation. But for water, when water is the solvent, we specifically call it hydration, okay? So this is an important concept to understand.